So, okay, let's talk about limits. So suppose you want to find the limit as x approaches c of k, right? So here, the whatever goes in here in this space after the limit, that's your function. So if what you have there is k, then your function is y equals k, right? Well, let's take a look at something like that, okay? Suppose, y equals k is any number, like y equals 3, y equals -2, y equals 5. If we were to graph y equals 3, how does it look? Like that, okay? All right, now suppose you had a value c. As x approaches c, what's the limit of this function? So immediately to the left, what's the limit? 3. Immediately to the right? 3. Well, it happens to be this, doesn't it, right? Because it's a straight line, constant value, no matter where you are, the limit is always going to be that same value. So the limit of a function is always the value of the function. So here, if I wanted to find the limit of 3 as x approaches 2, right? If this is x equals 2, the limit would just be 3. Okay? Now, what if you have the limit as x approaches c of x, this time y equals x, right? So let's graph y equals x. What does it look like? It looks like this. Okay? As I approach 4, what does the y value approach? Or 4, right? As I approach -2, what does the y value approach? -2, right? So in this case, if the function is x, then the limit is just the number that you're looking at, right? So for example, the limit of x as x approaches 3, well, if this is y equals x, as x approaches 3, the y value is just going to be 3, right? So the limit is just 3. Okay? All right. So let's talk about some broad limit properties. Suppose you have two functions, right? The limit of one function as x approaches a number is L. The limit of the second function as x approaches the same number is M. You have two functions. The limit of one at a point is L, the other one is M. Well, what we can do is, if you want to find the limit of the sum, you just add the limits, right? If you want to find the limit of the difference, subtract them. And then same with multiplication, division, and so on, okay? So for example, if you have the limit as x approaches 3 of x, what did we say that was? 3. And if I wanted to end the limit as x approaches 3 of 5, what is that? Is it 3? It's 5, right? Because now this is y equals 5. Right? So this we said 3 was, and 5, which is 8, right? But now, if I combined it, and if I said the limit as x approaches 3 of x plus 5, it's the same thing. The limit of x is 3. The limit of 5 is 5. You add them and you still get the same number. That's what the properties are talking about. It has to be to the same value, yes. Okay, so let's actually get into it now. I want the limit as x approaches 2 of 3. This is the one we just did, right? We said it was just 3, right? Then I want the limit as x approaches root 2 of e. Okay, what's the function here? Y equals e. What does that graph look like? It's still a constant. It doesn't matter whether it's 3 or e or pi. They're still just constant. So what's the limit going to be? E. Right? The whole square root of 2? Just, to make it fun. Okay, now let's start with finding, let's make it a little bit more exciting, right? Let's talk about functions, actual functions, right? So there are many different types of functions. Let's start with polynomial functions. If you want to find the limit of a polynomial function at x equals c, all right, all you have to do is plug it in and use direct substitution, right? So you can just use direct substitution for the polynomial functions, okay? All right. If you have a rational function, which is when you have like a function over another function, again, you can use direct substitution, except now we have a problem. If you have a rational function and you use direct substitution, you just plug in the value, we have a problem if the denominator becomes 0. That's when we use other methods, all right? So if the denominator is 0, then the limit cannot be found by direct substitution, okay? All right, so let's see what we can do here. All right, so for this one, it says to use direct substitution to evaluate each limit. So here's what you do. You want the limit as x approaches 2 of this. Direct substitution means literally just plug in 2 for every single x value. Now, here it is. This is the big one. This is where people lose points. The placement of LIM, that limit symbol, is super, super important. The minute you plug in your values, the limit symbol has to disappear. So when I plug x equals 2 into these x's, I just get 2 minus 3 over 2 times 2 squared minus 2 minus 15. Okay, so that's negative 1 over 8 minus 2, 6 over negative 9, right? 1 over 9. Okay? So do you see how the limit symbol here disappeared the minute I plugged it in? That is an actual thing. All right, so let's do another one. That's it. It's just 1, 9. All right, let's do one more. The next one, we're going to plug in negative 1 into here. So I get the square root of negative 1 plus 3, which is the square root of 2, and that's it. No. As soon as the 2 goes in, the limit literally disappears. It just goes away. Okay. And then, all right, so let's do this one. So if you plug it in, right, we get the square root of negative 8 plus 6, which is the square root of, negative 2. And that's an imaginary number. That's not a real number. That can't happen. So we say DNE. No. Because the limit can only be a real number, right? Remember, what is the limit? The limit is a value that the graph is approaching, and it can't be imaginary. Well, let's take a look at this for a minute. X plus 6, right? If this is negative 6, this is how that graph looks, right? What is the limit asking us? It's asking us for the limit at x equals negative 8. There is nothing there. That's just barren land, right? There is no graph there for there to be a limit. So that's the reason why it's DNE. Okay, here, the limit of this polynomial as x approaches a, right? So don't let that faze you. This is what we plug in, and you get 2a squared minus 5a plus 3. That's it. That's an actual value. Okay? Questions? All right. Now, sometimes things are not as rosy, right? Sometimes things just don't happen to work. When you use direct substitution and you get 0 over 0, right? You have a rational function. You plug in 2, you get 0 on top, 0 in the denominator. We call that indeterminate form. Because what's 0 over 0? Is it 1? It's not 1 because there is no quantity. It's technically dividing by 0, right? But 0 over 0 is indeterminate because when you have a function that results in 0 over 0, it might result in an actual limit, it might be infinity, or it might be DNE. So we don't know until we do some more stuff to it, okay? What we have to do is use other methods to find the limit, okay? All right, so there are several things we can do. One solution is factoring. We know how to factor. Let's factor. All right, so take a look at this. You plug in x equals -2, and I promise you get 0 on top, 0 on the bottom, right? One way to note that is we can do this. Put like a little 0 over 0 on top of the equal sign. That's a different situation. If you get 12 over 0, which we'll see, that's infinity. That's a different situation. But 0 over 0, this is only for 0 over 0. Okay, so now what you're going to do is you're going to factor. All right, the denominator can't be factored, but you have to factor the numerator. Okay, so look, here's what happens. When you're going to work with the function, you're not plugging in the numbers yet. That limit must stay. Okay? All right, so the denominator just stays as is. Okay, the numerator, we're going to factor by grouping. How do we know to factor by grouping? 4 terms, cubic term. Factor by grouping, so in the top and to the left, I factor out an x squared, and I get x minus 3. And then I factor out a minus 4, x minus 3. So this is the limit as x approaches -2. X minus 3, x squared minus 4 over x plus 2. Okay, I can factor that some more, right? So let's say this is limit as x approaches -2, x minus 3, x minus 2, x plus 2 over x plus 2. Okay, look at what happens now. This is it, this is it, this is it. Remember how we were getting 0 over 0? Look, you cancel them out. What was giving you a 0 in the denominator just went away. You removed the problem, right? So now what you have left is the limit as x approaches -2, x minus 3, x minus 2. Now we plug in the -2, okay? You plug in the -2. When you plug in the -2, the limit symbols disappear. X minus 2, x plus 2. It's still here. The plus 2 is canceled. The x minus 2 is here. Yeah? So now we get -5 times -4. This is equal to 20. And that's the limit. Okay? All right. Now, if you want full credit, your limits have to be exactly as they are now. If you neglect to, like if you forget to put these limits, -1 every time. Yeah, it's a big one. This is a big one. It's a big one. Huh? Okay, you're not allowed to. if you have a limit here, whoa. If you have a limit here, that's also minus 1, right? Okay, so that was another thing. Now listen, if you are confident enough, right, like if you can skip some steps here in the middle, that's fine, right? I mean, I know you know how to, I expect that you can factor. Yeah? Okay. All right, so let's do another one. This one we'll do a little bit more quickly. When you plug in the x equals 6, right, let's just plug it in just for fun. 36 minus 42 plus 6. 3 times 36 minus 66 minus 42. It's 0 over 0. Okay? It's indeterminate. So now, limit as x approaches 6, factor the numerator, x minus 6, x minus 1. Factor the denominator, 3x plus 7, x minus 6. There's got to be something for them to cancel out, right? Otherwise, you know. Yeah, exactly. You wouldn't even have had an issue. So those go away. So now I have limit x approaches 6, x minus 1 over 3x plus 7. Do write that final step, just so with all the crossing out, you don't lose sight of numbers and negatives and stuff, right? Now I can plug it in, and I get 6 minus 1 over 18 plus 7. And of course, you can skip that step. You can just go to 5 over 25, 1/5. Okay? Again, limit, limit, no limit, no limit. Okay? All right, so that was one thing, one way to solve, or to get rid of your indeterminate form problem. So you see how, like, you got 0 over 0, scary thing, but the limits actually turned out to be cute little functions, okay? I mean, cute little numbers. You, like for homework? Okay, for homework, you would have to write this, show me all of the work, and then the final answer. You've got to show me the work. Okay. The next solution, the next way to solve an indeterminate form problem is by rationalizing. Okay? All right. So here, look, when you plug in a 25, right, you get 25 minus 25, 0. Root 25 is 5 minus 5, 0 over 0 again, right? So now you have to rationalize this. You have to get rid of that root. The way you do that is you have to multiply this by the conjugate. What is the conjugate of root x minus 5? You guys remember? Root x plus 5. And of course, you have to do the same thing here. Okay, limit as x approaches 25. The denominator, please use the shortcut, a squared minus b squared. Square the first one, x squared, x, minus square the second one, 25. Okay? All right. The numerator. Okay, the numerator, I know you guys have that urge to FOIL that. Don't. Something beautiful will happen, right? Look at what will happen. X minus 25, root x plus 5. What happens? It cancels out. Beautiful. So now I have the limit as x approaches 25, root x plus 5, and that is just root 25 plus 5, 10. Tell me that's not like the most beautiful thing you've seen. It would be a lie. It would be a lie if you did. Huh? You still like it? Well, that's because of your like computer stuff. Yeah. All right. Here we go. plug in a 0, you get 2 minus root 4, 0 over 0, indeterminate. Hey, listen, sometimes there is a trick question out there where you plug in the number and you don't get 0 over 0. So please just plug it in first. Save yourself the headache because you don't want to do anything else otherwise, okay? And it's not correct in most cases, in all cases. Okay. So we're going to multiply by 2 plus root x plus 4. Okay. Limit as x approaches 0. In the numerator, square the first number, 4, minus square the second term, x plus 4. Placement of parentheses is key. X times 2 plus root x plus 4. Okay? All right, let me condense here. What do we get here when you distribute? 4 minus x minus 4, right? And then the 4's go away. So somebody tell me, what do we have left on top? Negative x over x, 2 plus root x plus 4. 35% of students, and that's not even like a random number, 30 to 40% of students will forget that negative. Okay? Now look, x's go away, but the negative stays. Yep. So now I have the limit as x approaches 0 minus 1 over this mess. Now I plug in 0. 2 plus root 4, 1 over 4. Negative 1 over 4. Okay? We talked about limits at infinity, right? Like using the graph, remember? And I think you guys are pretty comfortable with that. When we talk about the algebraic method, right? So suppose you have a function like this, right? And when you want to talk about the limit as that function approaches, as x approaches infinity, well, suppose your limit is the limit as x approaches infinity of 3x to the 7 minus 2x cubed minus 5x. And suppose now x is infinity, like a billion. A billion to the power of 7, right? That's a lot of zeros. A billion cubed compared to that is almost negligible. It's like nothing, right? So at infinity, we can ignore all of the terms except for the term with the highest power, okay? And so that's what we use for infinity. All right.